What specific problem does the SWYCC method aim to solve, and how does it address the limitations of existing approaches like MSE and GAN-based autoencoders?
The SWYCC method aims to solve the problem of blurry reconstructions in image autoencoders, which is a common issue with traditional pixel-level loss functions like mean-squared error, MSE, that favor low frequencies over high frequencies. To address this limitation, SWYCC employs a diffusion loss that is theoretically connected to KL divergence, allowing it to generate crisp results with high perceptual quality. Unlike GAN-based autoencoders, which are challenging to train and produce deterministic outputs, SWYCC's architecture incorporates a U-net decoder that can sample details at test time not encoded in the latents, enhancing diversity in outputs. Additionally, SWYCC achieves lower reconstruction distortion across all tested compression levels compared to state-of-the-art GAN-based methods, demonstrating its effectiveness in generating high-quality images. The method also benefits from a simpler training process without the need for tuning complex GAN-related hyperparameters.
How does the proposed method SWYCC work? Illustrate the main steps of the algorithm, including the roles of the encoder, diffusion decoder, and additional components like $D_initial $.
The proposed method SWYCC operates by utilizing a diffusion loss to learn an autoencoder architecture that consists of an encoder and two decoders, D_initial and D_refine. The encoder, which is a fully convolutional network based on ResNet blocks, compresses the input image into a latent representation. The diffusion decoder, D_refine, is a U-net architecture that refines the latent representation to generate high-quality reconstructions. Additionally, D_initial serves as a secondary decoder that takes the latent representation and the corrupted input to produce a pseudo-reconstruction, which aids in training by allowing the model to concatenate the corrupted input with its reconstruction. This setup enables the model to sample details at test time that are not encoded in the latents, ultimately achieving lower reconstruction distortion across all tested compression levels compared to state-of-the-art GAN-based autoencoders.
Can you provide a concrete example to illustrate how the SWYCC algorithm processes an input image through its architecture and what each component contributes to the final output?
The SWYCC algorithm processes an input image through a structured architecture comprising an encoder, two decoders, and a diffusion loss mechanism. Initially, the input image, X, is passed through the encoder, E, which is a fully convolutional network built from stacked ResNet blocks, resulting in a compressed latent representation, Z=EX. This latent representation is then utilized by two decoders, the initial decoder, D_initial, which reconstructs a pseudo-image from the latent space, and the refinement decoder, D_refine, a U-net architecture that enhances the reconstruction by sampling additional details at test time. The diffusion loss is applied to the corrupted input, X_T, and the output of D_initial, allowing the model to learn to denoise and generate high-quality images. This multi-component approach enables SWYCC to achieve lower reconstruction distortion and better perceptual quality compared to traditional GAN-based autoencoders.
What experimental metrics did you use to validate the effectiveness of SWYCC, and how do the results compare specifically to the performance of GAN-based autoencoders?
To validate the effectiveness of SWYCC, we utilized the CMMD cumulative mean maximum distortion metric, which correlates well with human perception, and the FID, Frechet inception distance, for assessing the quality of generated images. The results indicated that SWYCC consistently achieved lower reconstruction distortion across all tested compression levels compared to state-of-the-art GAN-based autoencoders. Specifically, as the relative compression ratio increased, the performance gap widened, demonstrating that SWYCC maintained better image quality and detail retention. Additionally, our approach improved FID scores by over 12% compared to GAN-based methods, suggesting that the latent space modeled by SWYCC is more effective for image generation. Overall, SWYCC outperformed GAN-based autoencoders in both distortion metrics and perceptual quality, confirming its superiority in image reconstruction tasks.
What were the key findings in terms of visualization and quantitative results, such as CMMD and FID, that demonstrate SWYCC's advantages over previous methods?
The key findings demonstrating SWYCC's advantages over previous methods include significant improvements in both visualization and quantitative metrics. Specifically, SWYCC achieved lower reconstruction distortion across all tested compression levels, as measured by the CMMD metric, which correlates better with human perception compared to the GAN-based autoencoders. Additionally, SWYCC improved the Frechet inception distance, FID, by over 12%, despite using an identical encoder architecture, indicating a more effective latent space modeling. Visual evaluations showed that SWYCC produced crisp images with detailed textures, outperforming GAN-based methods, particularly as the compression ratio increased. Overall, the results highlight SWYCC's ability to generate higher quality reconstructions without the need for complex GAN hyperparameter tuning.
What limitations did you encounter with the SWYCC method, particularly regarding generalizability or performance under certain scenarios? And how does the future work, suggested in the paper, aim to address these?
The SWYCC method, while effective in achieving lower reconstruction distortion compared to GAN-based autoencoders, faces limitations in terms of generalizability, particularly when it comes to high-frequency texture modeling. The paper notes that despite the improved performance, the latent space created by SWYCC may not be as robust as desired, especially under varying compression ratios, which can lead to performance degradation at higher levels. Future work suggested in the paper includes exploring better auxiliary losses, such as the DISTS loss, which could enhance reconstruction quality, particularly at higher compression ratios. Additionally, the authors propose further investigation into the latent space modeling to improve the overall performance and generalizability of the SWYCC method. This exploration aims to refine the approach to better handle diverse image characteristics and maintain high-quality reconstructions across different scenarios.